As we've seen, the energy levels in these hydrogen-like atoms and ions, uh, they are highly degenerate, and so we need to count the degeneracy of a given energy level E sub n. And again, we're looking at the energy levels, but for a given value of n, I have all of these L states that are different sets of quantum numbers and all of these m sub L states. So there's really a significant amount of degeneracy of the respective energy levels. So let's see if we can count them and see exactly how many are there. Remember, m sub L goes in integer steps, plus or minus 0, plus or minus 1, all the way up to plus or minus L. And one reason I like to write it this way is if you look at this, I've got 1, 2, all the way up to L, so I've got a total number of states. I'll get a plus or minus, and I've got L of these terms, so there's a total of 2L. The 2 comes from either plus or minus, and then the L, if I just count this, is 1, 2, all the way up to L, and that gets L. And then the m sub L equal to 0 is just a 1 state. So if I count up all of these, for any given L, I've got 2L plus 1 m sub L states. So what you can immediately say is that G sub L, the degeneracy of the Lth level, is 2L plus 1. However, for a given n, one has L goes from 0 all the way up to n minus 1. So I need to sum up all of these from L equal to 0 up to L equal to n minus 1 for a given n. And since G sub L is 2L plus 1 from the previous, we get this. And if I write that out, what it looks like is this. When L is 0, I get 1. When L is 1, I get 3. When L is 2, I get 5. So this just keeps going. And the very last state, if you look at it, is going to be 2L, but the last state is n minus 1, so 2n minus 1 plus 1. If you look at that, I'm going all the way from 0 up to n minus 1. And so there's n minus 1 from 1 to n minus 1 plus 0. So there's, if you count them, there's going to be n terms in this sum. Now, if you look at that, that is what the mathematicians would call an arithmetic sum. And the arithmetic series and arithmetic sum, the difference between any two terms is always a fixed amount. And here we're going up by 2's each time. And so this is an arithmetic sum. You can go and look up the formula for arithmetic sums, but I never remember it. So rather than look it up, what I do is I just derive it each time. If you look at this, what I'm going to do is I'm going to write this series out just like I have up here, the sum of all of these. It goes up by 2 each time, or the very top one. If I look at that, that's going to be 2n minus 2 plus 1, or if I add all that up, that just is 2n minus 1. And the previous one, since I'm going up by 2 each time, the previous one had to be 2n minus 3. So this gn I could also write in this form here. Again, it's n terms, starting here and ending here. And then I can rewrite that right below it here, and I just go in the opposite direction. So I write it in the opposite order. It doesn't matter what order you sum numbers. So I'll go 1, 3, 5, this 2 I write here, and finally go to 2n minus 1. So I add them up in the reverse order and rewrite that. That also has to be gn. And now that I just add these two equations, so everything on this side, gn and gn is 2gn. But if I add these terms side by side all the way up, I'll get 1 plus 2n minus 1, so that will be 2n. I'll get 3 plus 2n minus 3, well, that will be 2n. Keep going, they'll all be 2n. The next to the last term over here, when I add these two, 2n minus 3 plus 3, I'll get 2n. And the very last one over here, I'll get 2n minus 1 plus 1, or 2n. So these n terms are all the same, 2n. That happens for all of these arithmetic series. And then obviously, rather than adding them up, if I have 2n and I've got n of them, then I can get the whole sum here as just the number of terms times the value of each term, which is 2n. And that gives me the dividing through by the 2. I see that the total degeneracy of the nth level is just n squared. And so we found a fairly significant degeneracy formula. You probably have seen this before, but now you know where it comes from. The energy level of the nth state is this, and that state has a degeneracy of whatever the n value is squared. So if this were the first excited state, that n would be 2. And the degeneracy of the first excited state would be 2 squared, or 4. On the other hand, if this were 3, that would be the second excited state, then the n is 3, and the degeneracy of the second excited state is 3 squared, or 9. So it goes up very rapidly. It goes up as the square, the degeneracy does, in these atomic hydrogen-like systems.